Look at this split screen. On the left, we see a standard dark mode terminal running a single prompt and wait interaction. But here is the modern reality, a bifurcated interface where a developer works synchronously on one side, while a macro-level dashboard orchestrates 5 parallel tasks on the right. For decades, developers have operated as conductors. They guided a single synchronous AI assistant, waiting for a response before asking the next question. That linear sequence acted as a strict ceiling on output. A single context window can only hold a finite amount of information before it degrades. You cannot fit an enterprise architecture into a single chat thread. The industry solution is the orchestrator model. Instead of typing to one assistant, the developer becomes a manager overseeing an entire ensemble of independent agents. These agents do not require real-time prompting. They receive a set of instructions, coordinate asynchronously in the background, and report back when the task is complete. The structural requirement for this model is strict contextual isolation. Each agent operates inside its own sealed environment. By isolating these agents, they achieve hyper-specialization. An agent tasked with writing database schemas only accesses the database files. It does not scan the front-end user interface repository. Scaling software development requires abandoning the conversational chat interface in favor of massive parallel execution routed through standardized communication protocols. Mastering this handoff between synchronous coding and asynchronous orchestration is the structural requirement for scaling an engineering team through autonomous agents. If we look at the engineering campuses of companies like Google, seen here, the internal standard has already moved past simple autocomplete extensions towards comprehensive agent managers like Google Antigravity. Executive leadership at top tech firms is actively investing billions to remove the human from the micro-execution loop, pushing for autonomous project completion. This is the interface for Gemini. Foundational reasoning models like this one now possess the necessary cognitive depth to power those asynchronous background processes for extended durations. The underlying intelligence can now handle multi-step planning and self-correction. Developers who continue treating AI as a reactive autocomplete will find their workflows obsolete. This diagram illustrates why the push for massive context windows is a trap. When you force a single agent node to process UI components, database schemas, and API routes simultaneously, the workspace fills with red context noise. As that red noise overflows, the agent enters a state of context contamination. It begins hallucinating variables and confusing architectural patterns because it is acting as a full-stack generalist trying to juggle disparate tasks. To solve this, the single node splits into a directed acyclic graph, or DAG. We establish a parent orchestrator at the top, branching out to isolated, specialized subagents for data, logic, and API execution. The parent orchestrator does not write code. It analyzes the main objective and delegates the work by passing highly structured JSON briefs down to the individual subagents. Basic subagent delegation is strictly top-down. The more advanced Agent Teams protocol introduces horizontal coordination. Under the Agent Teams model, the subagents share a central task ledger. They monitor dependencies and automatically unblock each other as soon as a prerequisite piece of code is finished. Notice these arrows tracing laterally between the lower nodes. The API agent can message the front-end agent directly to share a data contract, completely bypassing the parent orchestrator to prevent a communication bottleneck. True reliability in AI code generation does not come from a larger context window. It comes from strict architectural isolation and specialized delegation. Orchestrating multiple agents introduces a physical execution risk. If 3 autonomous agents attempt to modify the same routing file at the same time, the result is a catastrophic collision. This animation demonstrates the critical isolation layer, Git work trees. The central repository splits off into distinct isolated container branches, placing exactly one active agent node in each sandbox. With these working directories physically separated, the agents can generate continuous streams of code simultaneously. Their paths never cross, eliminating the possibility of a merge conflict.
Running multiple AI chats is not true parallelism. Unless agents are bound to strictly separated working directories, concurrent execution is impossible. Even with isolated environments, agents face a capability problem. They need to query live databases and run security scanners. But dumping raw terminal outputs into an agent's memory rapidly bloats its context window. This diagram introduces the Model Context Protocol, or MCP. The MCP server acts as a firewall, sitting exactly between the isolated agent nodes and the array of external databases and tools. When the agent requests a database schema, the MCP server intercepts the natural language request. It translates that request into an exact SQL query, executes it, and returns only structured JSON back to the agent. Parsing structured JSON is highly efficient for a language model. It extracts the precise schema data it needs without memorizing thousands of lines of raw, unformatted terminal text. Beyond efficiency, the Model Context Protocol enforces a rigid security boundary to protect the system from autonomous mistakes. As the agent attempts a destructive action, like dropping a production table, the MCP server intercepts the command and issues a hard block. The action is physically prevented from reaching the environment. MCP operates as the nervous system for the orchestrator model. It grants agents precise, readable capabilities while maintaining absolute isolation and operational security. Inside these isolated work trees, agents execute a continuous operational cycle known as the Ralph loop. The loop begins with a linear progression. The agent picks a single task from the ledger, implements the exact code required, and runs automated validation tests to check its work. Watch the final step in this animation. If validation passes, the agent commits the code. Immediately upon commit, the agent's memory cache is wiped completely clean before the cycle restarts. Purging the context window is a strict requirement. If an agent retains state data across dozens of sequential tasks, it accumulates confusion, inevitably leading to degraded logic and hallucinations. The stateless but iterative loop is the primary defense mechanism against cognitive degradation. The agent enters every task with a completely blank slate. In a multi-agent system, code generation is no longer the primary constraint. The friction point shifts entirely. The new bottleneck is the verification of the code being produced. This graph plots error accumulation. The linear curve is human error. The exponential curve is AI error at machine speed. Because AI agents don't feel friction or refactor, errors compound invisibly, pushing the curve upward until the system breaks. Deploying an army of parallel agents without a verification system ensures one outcome: you will build a critically broken system faster than ever before. To neutralize that exponential error curve, the system requires automated quality gates. Here, we see 3 heavy gates slam down, intercepting the red trajectory and flattening it to a safe, sustainable level. Gate 1 is plan approval. The system pauses, forcing a human engineer to review and approve the architectural blueprint before any code is authorized. Gate 2 relies on lifecycle hooks. These are automated continuous integration checks that serve as strict execution boundaries. A lifecycle hook physically blocks an agent from marking a task as complete until its linting and test coverage achieve passing grades. If the tests fail, the agent is forced to iterate. Gate 3 is persistent semantic memory. The agents maintain a centralized agents.md file to record session learnings, architectural rules, and specific syntax preferences. This persistent memory allows the agent network to compound its knowledge. It reads the file before starting a new task, ensuring that a systemic mistake corrected yesterday is not repeated today. The developer's daily routine shifts away from typing imperative lines of code or nursing a single chat prompt. The discipline becomes spec-driven development. The developer's primary job is to engineer precise, declarative specifications that outline exact constraints, acceptance criteria, and architectural bounds. The specification is now the ultimate point of leverage. To safely command a multi-agent orchestra, developers must stop writing the music and start